Okay, body temperature, mean body temperature 98.6, no surprise, standard deviation of 0.6. I'm not sure if we made that up or not. Don't ever believe any of the stuff we tell you in this class, because a lot of times we just make it up so the numbers come out good. 98.6 is the mean temperature, right? And the standard deviation, I'm putting you down here. I'll make believe I'm dealing with a population instead of a sample. 98.6, and the standard deviation is equal to 0.6. Okay. Okay, a little bit of twist we threw in there, right? You got a problem with this, don't we? Yeah, that's a problem. Yeah, that's exactly the point. Okay, let me take a look at this with you now. I don't want you to labor at it too much. Let's see, 99 degrees is going to be here, right? If I had said 98.6, if I had 99.2 instead and asked you what percentage of the population has a temperature above 99.2, that would have been pretty simple because that would have been one standard deviation above the mean, and you could have just said that that was our 16% again that we were looking at before, right? Problem now is that we didn't say that. We said 99, right? So that is not an even number of standard deviations above or below the mean. Similarly, 98 is not, no, 98 is. Yeah, 98 is. So what percentage of people in this population would have a temperature under 98? That's one standard deviation as before. So that's going to be, even though it doesn't look like it's 16%, right? How about between, I'm going to just for the moment, I'm going to say, 99 is a little bit more, was it 90? Yeah, 99 is a little bit more than one standard deviation. So it's a little bit further to the left. Let's call that 14%, just for argument's sake, just by eye, right? So if I asked you, what's the probability of having a temperature less than 98 or greater than 99? In other words, this area plus this area, you'd add 16 and 14 and come up with about 30%, right? Unfortunately, if it would have been one standard deviation above, we could have said 16 with a little bit more certainty, right? But I kind of just rounded it off for the moment. Okay, so that's a bit of a problem now because this works okay if we know exactly how many standard deviations above or below the mean. Doesn't work so well if we don't know that. Correct? Okay, so I'm going to close this now and I'm going to open up the next document. Okay, and this is where we're really going to wind up learning something that we're going to wind up using for the rest of the semester. Okay, and I'm going to open up document number C, which is on Blackboard again. Okay, and I'm going to open up something else. I'm going to open up, in a moment, I'm going to open up some tables. First, I want to get started on this next notebook. Okay, let's see, notebook. Okay, let me close this. Don't save. They're all closed. Okay, open. Okay, number 3. Good. Okay. Here's a distribution. Okay, so now it would really be valuable to us if we knew a bit more about how standard deviations worked and this normal distribution worked than just the empirical formula. Empirical formula is fine for estimating rough estimates of what the areas under this distribution are, what the probabilities are, right? But we need to know a bit more than that. So we're going to invent we're going to take by the way, all of this stuff is based on formulas. It's not just invented. Okay, come on. Okay, and here's the formula that that describes that line that you're looking at that we call the normal distribution. Okay, very similar to the, kind of similar to the equation that we use for the binomial distribution. If you look there, there's three unknown, f of x is the height of the line, right? We're really interested in the area under the curve, but f of x represents the y-axis, the height of the line. And the height of the line is determined by three things. It's determined by the standard deviation, that's sigma. You see it down there. It's determined by the mean, and it's two things. The mean, three things. The mean, which is mu, the standard deviation, which is sigma, and what's the x stand for? The x stands for the value at any point, like in other words, 99 degrees or how many inches or something like that. It's determined by the value of x, the point at which you want to know the height, right? The standard deviation and the mean. So those three things determine what that height is, what that probability represents. And this formula will give it to you, right? Well, obviously, we're not going to be using this formula to solve these kind of problems, but that's what this is all based on. So if you have a formula that can predict all these different possible outcomes for different standard deviations, you can then put together, you can create a version of the normal distribution. I'll go back to the previous page. You can create a version of the of the normal distribution where you say to yourself, gee, what would these areas look like if I said the mean was equal to 0 and the standard deviation was equal to 1? And use that formula to create a value which represents the area, right, for every different possibility for what the standard deviation, what the value of z is, what the value of the standard number of standard deviations is. If it were 0, when standard deviation is equal, when the number of standard deviations away from the mean is 0, when you're at the mean, you know that that's 50%. That's area represents 50%. When you're at one standard deviation to the left of 0, right, or at -1, right, well, that area represents about 16%. We know that from the empirical rule. But now we can calculate it using that formula for every possible value. There's two ways we can use that now. One way is to go to a book that has a table where these are all been worked out. And these are called z-scores. The z-score basically represents, let me write this down. The z-score, I don't know if this is technically the best way to describe it, but it basically represents the number of standard deviations from the mean, right? So a z-score of -1 is one standard deviation below the mean. Z-score of -2 is two standard deviations below the mean. +2 would be two standard deviations above the mean. So now we need a table that'll give us those areas. Okay, so let's get to a table. And this is on Blackboard also. Okay, well, actually, I want to show you I'm going to show you the table first, and then I'll go back in and confuse you. So no need for me to confuse you right away. Okay, so now here's my z table. Notice that the z-scores here are on the left-hand side. These are the z-scores, right? So I'm going to go to a z-score of 0. That's a negative z-score. The second page is all positive z-scores. So if you look at 0, right, -0, same thing as 0, right? What is that area? It's 50%. If I go over here, it's +0, it's 50%. What does that mean? That means that when the z-score is 0, when you're at the mean, right, that the area below it is 50%. Okay? So I can look up whatever z-score I want and determine what area is represented. On this particular version of the z-table, these areas in here, right, for instance, if I looked at the area for one standard deviation below the mean, the area to the left of that is 15.87%. Where did that come? What did we see before? We called it 16% when we were with but it's really 15.87. This is more accurate than the empirical formula. So what does that mean? That means that if the z-score is 1, the area to the left of that is 15.7%. Now, if the z-score is using these tables, if the z-score is a positive number, what's the lowest value that the percentage could be? 50%, right? It's got to be above 50% if it's a positive z-score, because a positive z-score means to the right of the mean, right? So what about a z-score of +1? A z-score of +1 represents 84%, right, or 0.84. How much is to the other side of that, right? Remember that 84% represents the area to the left of that z-score of 1. How much is left here? 16%, just like we were looking at before. And what about if I wanted a really oddball z-score? What was the z-score that we would have needed to calculate for 99 degrees? How big is the difference between the mean and 99 degrees? The mean was 98.6. 99 minus 98.6 is 0.4. And what was the standard deviation? 0.6. So it's 2/3 of one standard deviation, 0.67, let's call it, right? So where can I find a z-score of plus 0.67 here? Well, let's go take a look. This represents the first digit of the z-score, 0.6. Here's 0.6. Now it only gives me the 0.6. How do I get to the 0.67? Well, everything in this row is 0.6, and this represents the third digit, like 0. So 0.60 would be 0.72. That would be 72.57%, or 0.752. 0.61, 62, 63, 64, 65, 66, 67. So the area we're looking at the area for 99 degrees to the left of that is 74.86, right? So if I asked you, what's the percentage of this population that's above 99 degrees, what would you say? It would be 1 minus 0.7486. Okay, makes a little bit more sense when you draw it. Okay, can you guys visualize this, or by not drawing it, did I lose you a little bit? I got to draw it, right?
Just want to left to the on top is the second decimal place.
I'm sorry. Yeah, this is the right, or really it could be the second or third decimal place. So in other words, if you wanted to know the area to the left of a z-score of 1.25, it would be 1.201234 89% of the area of the distribution would be to the left of a z-score of 1.25. Okay, don't worry about it. We're gonna do a few examples that will cement this for you. Okay, but you might want to keep that table around. I'll keep it up. I'll keep it up there. Now, as far as the other thing I was going to show you is, let me go back to my notebook. The other thing I want to show you on here is, okay, I'm very unhappy with how slow this is starting to act. Okay, yeah, I was going to show you a standard normal distribution. I wanted to point out to you that there are many different versions of these tables, and you got to be a little bit careful. That's not one to resize it. See, there's a couple of different versions of this table. For instance, this one with the 2 pages, that's almost identical to the one we're using, right? It's always the area it gives you is always the area from that point to the left, below that value. Okay? You look up a z-score, it's going to give you the area of the distribution to the left of that value. Okay? This one on the right here does the same thing. Gives you the area to the left of that value. Okay? Except this one only bothers to give it to you in a single page because the table is symmetrical, so it only gives you 1/5 sides. Okay, how about this one over here? What does this one give you? This one gives you the area between the mean and the value that you chose for z. A little tricky, right? Okay, but they almost always have a diagram at the top that'll describe for you what area that they're referring to. Now, this one clearly will never be over 50%, right? Because you're never a bit bigger than the value from the mean to either one end or the other end. So this will never have a value greater than 50%. Okay, where this one, the one we use, could have a value over 50%, because it'll tell you that point all the way down. Even if we're all the way to 99% of the distribution, it'll tell you 99% is still left of me. Okay, so let's give this a try. Let's open up. Let me switch pages here so I got something to write on. Okay. Okay, and I'm gonna actually be able to draw on this and make more sense of this stuff. Okay, so I'll move this over here. So I'm gonna open up this third document that's on Blackboard to see if I can find it. Okay, and I'll post answers to all of these examples. So when you go home, you'll be able to work with them on your own. Let me just check online. You guys online keeping up with me? Can you still hear me? See the screen? Awake? Good. Okay. Put the cocktails down, okay? So that we can get through this last part. Okay, good. Let's see. C. Okay, let me open this up. Okay, let's try a couple of these examples. Okay, let's see. Assume that the heights of adult U.S. women have a mean of 63 inches and a standard deviation of 2 inches. What percent of women would you expect to have a mean height less than 63 inches? And we start with that one. We know that, right? 50%, right? Okay, less than 62 inches, right? So less than 62 inches, that's a little bit of a problem, right? Okay, let me bring this up here. So for this example, the mean is 63. The standard deviation is equal to, what was it? 2, okay? And we're interested in what percentage of women have a mean height less than 62 inches. So what's the z-score for the value of x, which is 62? Right? How many standard deviations below 63 is 62? 1 out of 2, right? 1/2. How can I do that if I don't want to remember this? Z is equal to x minus mu over standard deviation. Okay, so what is that? X is 62 minus 63 over the standard deviation, which is 2, which is equal to minus 1/2. Not 1/2, but minus 1/2. What does minus 1/2 tell us? It's on the left side of the mean. Okay, and we know so we want to know what percentage of women are what? Lower than that or less than that. Okay, so our table is actually perfectly set up for that because it's going to give us that area right away. Right, it's going to give us the area to the left of that. First of all, number one, we have to be at the top part here because we're dealing with areas to the left of the mean. So negative 0.5. Negative 0.5, 0.50 is this one. If it had been 0.51, it would have been this one, 0.52. So that's 30.85, 0.3085 is this area, 0.3085. Right? That's the area that we're talking about. That's the percentage of the population. That's the probability of you picking an individual randomly out of the population. That's that height or smaller. Right? So what's the next question? Okay, what's the third part of this? Greater than 66 inches. Okay, 66 inches. So that's going to be over here. Okay, so let's use our formula. Z is equal to x minus mu over sigma. Right, that's equal to x. 66 minus 63 over sigma, which is 3, 2, 2. Right, so what's that going to be equal to? 3 over 2 is 1.5. So our z-score, positive or negative? That's a positive, right? Okay, so what do we want to know? More than or less than? Greater than 66 inches. So we want this area to the right. Our z-table doesn't give us areas to the right, does it? Only gives us areas to the left of that z-score. Okay, let's take a look at what that's going to be. The area to the left of that z-score, 1.50, is 93.32. So the area from here down is 9.9332. Well, how do I know what the area here is? Bingo, there you go. Exactly. This is as hard as it's ever going to get, right? Okay, but you'll forget this in a week after we finish the semester, you'll forget. Okay, I promise. 8, what is that? 6, right? Carry 1, 6, 6.0668. That's that. That look right? Looks good enough, close enough, good enough. Okay. 6.68%. Remember, a little tricky because we had to flip this on its head because we only could use the table to give us the area to the right, to the left. So let me ask you this. Here's an interesting question. We already have all the data that we need for it. What's the probability of someone being between 62 inches and 66 inches tall in this population? Right, what did we figure out just now? We figured out the probability of being over 66 inches is this. The probability of under 66 inches is this. So what's the probability of being between them? It's going to be 1 minus 0.0668 plus 0.3085. Make sense? Right? We're going to take this area, add it to this area, and subtract it from 1. Right? And that'll leave us with that sliver in the middle. Okay? If I had asked you, what's the probability of being less than 62 inches or greater than 66 inches, I would have just forgot about the 1, just added these two together. Okay? Not hard, right? You guys do the next one. Okay, next one's number 2. Oh, that's the same problem, isn't it? Do number, did I repeat this? Yeah, do number 4. Number 4 is a twist. Let's see if one of you guys can figure it out on your own. A little bit different, right? You have all the tools you need to solve this problem right now. I'll give you a couple of minutes to work on it yourselves. Anybody online got the answer? Think logically now. Because it really is just logic, right? I'm going to get a fresh page here while you guys are working on that. Hopefully I have another sheet there. Yeah, I do. Okay, I'm going to show you how I would work this out. Okay, so what information do I have? I have that blood pressure has a mean of 120 for this population, whoever it happens to be. Oops. 120 is the mean, right? And the standard deviation was how much? Was 8. Whatever this is, millimeters of mercury, I guess, right? So it's 8 or centimeters of mercury. Millimeters of mercury. Millimeters, yeah. Okay, it's 8, right? So standard deviation is 8. And the question was, what blood pressure would you have to exceed to be in the highest 10% of this population? Well, let's see. In this population, normally distributed, what value for the blood pressure would give us an area in the top 10%? Right? I'm going to use the table backwards, right? If I go to the table now, and instead of looking at the z-scores as they did before, right? This time, instead of looking at these z-scores, I'm going to look at the areas. So I know it's going to be up here. So the z-score of that number is going to be above 0. It's going to be a positive number. It's going to be way up here. Right? So I'm going to go down here. And I'm going to find the area in here which represents 90% to the left. 10% above, 90% to the left. So where is 90% here? The closest z-score to 90% appears to be this one right here. So what is that? That's 128, right? A z-score of 1.28 seems to represent an area of 90% to the left. That leaves 10% to the right. Okay, so the z-score of this value that would give us 10%, that z-score is equal to 1.28. Right? Well, now I need to know what does that z-score represent? I need x, not z, I need x. Remember we had that formula, z is equal to x minus mu over sigma, right? So now I know what z is. It's 1.28, right? Positive 1.28 is equal to x minus the mean, which is 120, divided by the standard deviation, which is 8. The only thing left is x, right? So I can solve for x. So x is equal to 120, right, plus 8 times 1.28. Okay, so what I did there, right? I multiply both sides by 8, so that moves that 8 over there, and I moved the 120 over the other side, it becomes positive. So let's figure that out. Okay, so clear, 120. Right? I'm gonna hang on a second, I'll do it this way. 8 times 1.28 is equal to that plus 120 is equal to 130.24. So the blood pressure that would give us 30.24. That blood pressure is the blood pressure at which 10% of the population would be above that number. Okay? And 90% would be below that number. If I asked you what blood pressure would represent the point at which 50% of the population is less than that blood pressure. The mean, right? 120. How about 25% of the population was less than that blood pressure? Well, now we'd have to take a closer look at this, wouldn't we? 25% of the population, right? We need this z-score. And what is that z-score going to be equal to? Well, let's see. We have to find it on the table here. And we're going to go up and use our negative numbers for z now because it's on the left side. So 25% of the population would be, let's see, 25%, 0.250. Where is it? 0.25, looks like this number right here. It could be, actually, I want to look closer. Looks like 0.68, negative 0.68. Right, z-score is equal to negative 0.68. So now I'd have to figure out what value that represents. So z is equal to x minus mu over sigma, right? Z, which is 0.68, negative 0.68, is equal to x, which is what we're looking for, minus the mean, which is 120, over 8. So make sure you don't lose that negative sign in front of the 0.68 because it's a negative z-score, right? So what do we do this time? Well, this time it's going to be move 120 over to the other side. It's going to be 120 minus 0.68 times 8, right? It's going to be to the left. We've got to subtract. That's going to be to the left of that. Okay, so if I get my calculator, clear, that's going to be equal to 8 times 0.68 equals that, 5.44, change the sign, plus 120. I am subtracting from 120, it's 114 and a half. Okay, it's 50% of the population is going to be below that. And what percentage of the population is going to be between a blood pressure of whatever that was, 120 and 130? It's going to be whatever's left, 25, 35, 65% of the population. So you can manipulate this any way you want, which is good because it means that you have an enormous amount of power over figuring out what these areas represent, what probabilities there are when you're dealing with a normal distribution. The really important part is that as we move on, we're going to find that we can use this to make predictions about samples and populations, predicting whether or not one population is really different from another population using a sample. Gets a little complicated. We'll talk about that as we move forward. But this is really the basis for a lot of the stuff that we're going to be doing moving forward. I just want to show you one other way we can use this. I just want to make sure I don't have anything else over here I need to show you. Okay, and that is that if you don't have the table handy and you do have Excel, you can also use Excel to find the areas. Okay, let me get Excel. Let me go up here somewhere. I'll blow this up a little bit even more. Doesn't help on the too much to blow it up for this, because I think it still keeps the little descriptor small. Okay, this time I'm going to use a function called norm dist, hold in parentheses. Okay, and what does it come up with? It comes with x, the mean, the standard deviation, and cumulative. Okay, I'm going to go back to one of the examples that we just used and say 62 inches is x, 63 inches is the mean, and the standard deviation is, what was it? 2, I think was right. 2. And cumulative. Well, for cumulative, I'm always going to use true. Why am I always going to use true? You answered that question before. Why am I always going to use true for cumulative?
Because that's going to give you
the area right to the left. Why am I not going to use false ever? Because when we're dealing with a continuous variable, that it represents a line. That number represents a straight line, has no area, so it's meaningless. To say true here would be, to say false here, right, would be meaningless, right? Doesn't mean anything. That number doesn't mean anything. I'm going to change it to true. That area at that line really is not 17%. There's no area. That represents just that exact value of 62, which has no area, because it's like if you just draw it on here, it's just a straight line. So there's no area, so it doesn't work. Why did they put it there? I have no idea. You'd have to ask Bill Gates why they offered that as an option there for this particular one. So what does this represent? That represents that 31% of the population is below that value. Okay, so that's norm dist. How about norm s-dist? Another form, I'll give you a list of these. Norm s-dist is another function, parentheses, except this one just asks you for the z-score. What do you think it's going to return if you tell it the z-score? The area, right? So if I give it a z-score of 0, what's it going to return? That's the mean, right? Z-score. So yeah, it's going to return 50%, right? If I give it a z-score, norm s-dist standard distribution, right? It wants the z-score. Let's say I tell it that the z-score is -2. What's it going to give me? Z-score -2. Let's think about this. -2 to +2 is what area? 95% of the distribution. What does that leave? 5%. Is all of that 5% on the left-hand side? No, half's on the left, half's on the right. So what's to the left of -2? Half of 5% or 2.5%. There you go. It's a little bit. Yeah. The real value, which Levi mentioned before, is really 1.96, not 2. If I had put in equals norm s-dist, if I had put in -1.96, now this is going to come close to 2.5%. Okay, because that's really, if you ignore the empirical formula, the real value is closer to 1.96. Okay, that's important to us because in statistics, when you read a study, what do they always say that their acceptable level of error? Well, they always say this thing alpha error equals this, 0.05, right? 5%. You're willing to accept 5% chance of being wrong. This is where your 5% comes from. 2.5% on the low side, 2.5% on the high side. As we move forward, this is really going to have an impact on everything we do.